A warm good evening to everyone present here, and welcome to day 2 on this bootcamp on calculation of cell parameters. So yesterday was day 1, and we looked at cell basics, some basics of electrochemical cells. We looked at some of the electrochemical reactions that took place within the cell. And we also looked at some of the properties, some important properties of lithium-ion cells, and we concluded by seeing why lithium-ion cells are preferred in today's market. So in today's session, we are going to be dealing with some simple basic calculations of cell parameters. Okay, so let's get started. And for today's content, we will be dealing with these many parameters. So we'll be calculating all of these parameters. So starting with basic calculation of cell total potential. So we'll be using and the Gibbs energy, the Gibbs equation to find out the total cell potential, and then the cell capacity, which has a specific equation that is dependent on some of the active material present inside the cell. Then we'll be calculating the cell energy, and just as an example, to calculate the total number of cells of a battery pack and the mass of a battery pack. Okay, so these are the few parameters that we'll be calculating, right? So let's first look at some important terms before we proceed into the calculations part. So we know that in a cell, there are two main reactions that happen. One is reduction reaction, and the other one is called as oxidation reaction, right? So the oxidation and reduction potential refers to the measure of the amount of voltage contributed per reaction. Okay, and therefore it can also be said that reduction potential basically is a definition of how easily any element or any material can gain or lose electrons. Okay, so a high reduction potential, or any element or any material, any metal with a very high reduction potential, basically is nothing but it is able to gain electrons easily, or it is able to accept electrons easily. Okay, while a lower reduction potential corresponds to any metal or any element to lose electrons easily. Okay, so conversely, we can also write high reduction potential as low oxidation potential. Okay, so basically that means that its ability to lose electrons is very low. Okay, and also a low reduction potential would correspond to a high oxidation potential. Okay, so as I said, potential is nothing but the measure of the amount of voltage, or the measure of how much of electrochemical potential a particular reaction can provide at a particular standard temperature. Okay, so in this entire session today, we'll all be referring to all of the parameters and all the values at 25 degrees Celsius, which is ambient temperature or room temperature. Okay, so at different temperatures, we'll also have to consider the change in active material concentration and all that. We will not be doing that. So we'll only consider 25 degrees Celsius room temperature. Okay. So with these two terms, that is with reduction potential and oxidation potential, we can then calculate something called as the reduction standard potential. Okay. The standard reduction potential is basically the difference or the sum of each individual potential. Okay, so the potential contributed by the reaction occurring at the cathode and the potential due to the reaction occurring at the anode. Okay, so if you take the difference of these two, we get something called as the standard potential. Okay, so this would be the case. This would be the case only if we had equal concentration of anode and cathode. Okay, so there is something called as active material concentration. Okay, so yesterday in the session I had talked about active material, right? So there is also something called as active material concentration. that talks about how much amount of active material is present. Okay, so with relative to the electrode and with respect to the electrolyte as well. So how much active material is present? That is basically what is molar concentration, simply explained. So that would be the case if 1 mole of concentration, meaning active material is the same in both the anode and the cathode. Okay, so we know that is generally not always the case. There will be some difference. Okay, so which is what we'll be seeing in the upcoming slides. So exactly how this particular equation will change with respect to also change in molar concentration. Okay, so this is the basics about reduction and oxidation potential. It is important to note this, and with this we will progress to the table that shows what are the different reduction potentials of different elements. Okay, so here are few of the elements. There actually this list is shortened. There are like a numerous number of elements, like more than 200 to 300 different types of elements and compounds all put together, which have different electrode potential. But for today's session, we'll try to keep it simple. We'll restrict ourselves to one simple example. Okay, so that'll be zinc and copper. And what I will do, I will solve one set of numericals, set of equations for you. And based on the same process that I have solved for you, I'll give you another example on a lithium ion cell, and you can perform the calculations and let me know on the results, within some time. Okay, so now let's take a look at how exactly change in active material concentration can lead to change in cell potential. Okay, so that is given by something called as the Nernst equation. Okay, this one, this is here the Nernst equation. This equation basically relates your total cell potential to your standard cell potential at 25 degrees, your number of electrons participating in the reaction, the Faraday's constant F, and something called as the reaction quotient K. Okay, so this reaction quotient K is exactly what describes the change in molar concentration. Okay, so K is nothing but the ratio of anode to cathode concentrations. Okay, so we will see this in the terminology over here. Okay, so I'll explain the complete reaction. I'll also tell you how this particular equation has been derived. Okay, so we can start with this particular Nernst equation. Okay, so as I said, it is a equation that relates the total cell potential. E cell is the total cell potential. E naught cell is the standard cell potential. R is the universal gas constant. T is your ambient temperature. N is the number of electrons participating in the complete reaction. So in your entire redox reaction. F is a constant called as the Faraday's constant. And K, as I said, is your molar concentration ratio, or also called as reaction quotient. Okay, so let's take a simple example, okay, of zinc and copper, and we'll try to solve a few numericals based on that. Okay, so first, before that, let's have a quick derivation on this. So this particular equation, the Nernst equation, has been derived from something called as the Gibbs free energy equation. Okay, so Gibbs free energy equation. Okay, so what does Gibbs free energy equation look like? So it's basically given by delta G is equal to N F. It is a product of the number of electrons participating in the reaction, the Faraday's constant, and your cell potential E cell. Okay, this is your total cell potential E cell, and delta G naught is equal to NF E naught of cell minus RT into logarithm of the reaction quotient divided by N into F. Okay, so if you were to take the addition of these two, or if you were to take the complete if you were to equate these two, then you would get NF. Sorry, this is by mistake. It doesn't come in the denominator here. So NF of E cell is equal to NF of E naught of cell minus RT ln of K. Okay, so if you were to equate these two, if you were to equate delta G and delta G naught, then you get NF E cell is equal to NF of E naught of cell minus RT ln of K. Okay, so dividing the entire equation by NF, so what you would get? You can simplify this. So divide by NF. So your final equation would then look like E cell is equal to E naught of cell minus RT by NF ln of K. All right. So this is how you're able to derive your Nernst equation. And that is, as I said, derived through the Gibbs free energy equation. Okay. So this is basically how this equation is derived. So with this simple derivation, we will then proceed to the numericals. So first, let's take a simple example of zinc and copper. Okay, so all your constant variables have been mentioned here. So R with 8.314 joules per Kelvin per mole. F is the Faraday's constant at 96,500 coulombs. T is the ambient temperature, which I said is 25 degrees Celsius. So let's take this in Kelvin. That will be 298 Kelvin. Okay. So N is the number of atoms. Number of electrons, not atoms, number of electrons participating in the reaction. So this depends on what kind of reaction we are looking at. If it's a simple reaction that is pertaining to zinc and copper, then the number of electrons will be like limited to 2. But other reactions will have different kinds of number of electrons participating. And then finally, E naught of cell will be a sum of the standard electrode potentials. So we will see one by one what are the electrode potentials. Okay, so you can see over here, these are the electrode potentials mentioned. Okay, so we'll see this example in the next slide. Okay, so let's take zinc as anode and copper as cathode. So the same example as we had seen yesterday, the Daniel cell. So from the same example, we will calculate all of the parameters. Okay, so zinc reduction potential or your anode potential, anode standard potential, anode standard potential, and copper reduction potential or your cathode standard potential. Okay, so these are your individual electrode potentials, and these are your molar concentrations. Okay, so let's apply the Nernst equation and we will find out the total cell potential given these values. Okay, so let's first calculate what is called as the standard cell potential or E naught of cell. Okay, so that is E of cathode minus E of anode. Okay, so that would be 0.34 minus so that will be around 1.1 volts. Okay, so this is your standard cell potential, but this is not your total cell potential. So for that, we have to calculate first the cathode, the ratio of cathode concentration to anode active material concentration. So I had mentioned the values given over there. So 0.85 upon 0.05. You can write down all of these values with me. Please do write this down. So what will be the reaction quotient value over here? It will be 0.85 by 0.05. So that is 17. Okay. And we can substitute all of these values. So K, we can substitute over here. And E naught will go over here. Okay, so your E cell will then be equal to 1.1 minus divided by N will be 2 into 96,500. So I'll explain how exactly N is 2. So let's consider the redox reaction occurring in the cell. Okay, so as we had seen in the example yesterday, zinc gets oxidized to zinc 2 plus 2 electrons, right? And copper 2 plus CO2 plus 2 electrons becomes copper, right? So by observing this particular reaction, that is how we get to know N is equal to 2. So N is nothing but the number of electrons participating in the complete reaction. Okay, so that is how N is equal to 2, and 2 into 96,500 into ln of 17. Okay, so you have to do ln, which is natural log, not log to the base 10. Please do ln. So once you perform this calculation, can you please type it up in the chat box? What are the answers each one of you are getting? If your calculation is right, it should be 1.06 volts. Are everyone getting this answer? 1.063, yes. So this is waiting for a few more replies, and then I'll progress to the next parameter. Okay. So then I will progress to the next part. So 1.06 volts is what you will get. Okay, so please make a note of this. We will be utilizing this value in the further calculations. So this is how you will calculate your total cell potential. Okay. We will then see how to find out cell capacity. Okay, so your cell capacity is nothing but the sum of the capacity contributed by each or individual active material. Okay, so we'll have the contribution of active material from the cathode and of the anode. Okay, so for that you will need what is called as the molecular mass of the contributing electrode material, right? So your N and F values will stay the same. Okay, so your N will be 2 and F will be 96,500, while M cathode and M anode will be dependent on these values. So you can see these are the molecular mass of each element, each electrode that I have mentioned over here. Okay, so let's write this down. So capacity of cathode is equal to 2 into 96,500 divided by your M cathode, which will be 63.4. Okay, so you can type the answer here in the chat box. Let me know. While C anode will be 2 into 96,500 divided by this value. So that is 65.8. And can you tell me the answer for both of them? 3044.16. Yes. Okay. And 2933 would be for your anode. Okay. And units for these are milliamp hours. Okay. Not amp hours. This is milliamp hours. So with these two values now that you have obtained the capacity of the cathode of each electrode, that is of cathode and anode, you can go ahead and substitute both of these values in this final equation over here. Okay, the last one. So you can substitute them here, and your final answer, that is your total cell capacity, which I'll write here, C cell, will be, I think, 1,419 milliamp hours. Okay, can So whoever has done the calculation can write this up in the chat box. Please do be interactive. So is everyone getting this answer? Okay. So with that, I hope you have been able to follow for the cell capacity. So whatever value that you're obtaining over here is purely dependent on the molar concentration and the molecular mass of each element of zinc and of copper. So this is specific to these two values provided here. Okay, so for different values for different molecular masses, you'll get different capacities. Okay, so with that, we will proceed into the next point. So I hope that so far you all have understood how to calculate the cell capacity. Okay, so cell energy. So basically, cell energy is how much of capacity it can output per in order to produce some useful work. Okay, and that is basically a product between the cell voltage and your capacity. So what is the voltage we have obtained? It is 1.063 volts into 1419 amperes. Okay, so what would be our final value here? What would the final answer? It will be in watt hours. So if you were to take the product of this, you would get, so on 1.51 watt hours. Okay, so our answer will come as 1508, but that will be in milliwatt hours. Okay, that will be in milliwatt hours, and if you convert it to watt hours, it will be 1.51 watt hours. Okay, so this is your cell energy. Okay, so we have found out three of the most basic parameters over here. So that would be your cell voltage, okay, so then your capacity, and your energy. Okay, so to summarize, these are the different values we'll get, right? So utilizing the given data from the reduction potential chart, we have been able to obtain these values for a simple zinc copper cell. Okay, so now what I'm going to do, I am going to provide some of the data, some reaction data, and some molar concentration data for a lithium metal oxide cell. Okay, so I will not be performing the calculation. You all will be performing, and let me know in the comments what in the chat box what exactly are the answers you're going to get. Okay, so I will write down the reaction for you, and I will provide the molar concentration, the molecular mass, and the temperature values. Okay, so with that, let's first understand what I mean by LMO. So LMO is lithium metal oxide. So this is basically the lithium metal oxide is nothing but your active material that is present within lithium ion cells. Okay, so basically it is a combination of lithium and some form of a oxidized metal. Okay, so usually it would be something like lithium manganese cobalt dioxide, okay, or lithium manganese aluminum dioxide. Okay, so usually it would be one of these two, or it could also just be lithium cobalt oxide. So whatever metal composition is there, it can just generally be expressed as LMO. Okay, and I'm going to be providing the reaction values for this along with some of the other important data. Okay, so so the reaction goes like this. At the anode, okay, at the anode we have oxidation of lithium carbide LiC6. So we had seen this example in the previous session, in yesterday's session. So this breaks down into Li ion plus 2 electrons plus C6. Okay, so yeah, it's supposed to be two lithium ions here, not just one. So for this, your electrode potential is minus 3.04 volts. Okay, so this is at the anode. At the cathode, the reaction is as follows. So the same lithium ion that has been given out plus 2 electrons plus metal oxide will combine or undergo reduction to give you lithium metal oxide. Okay, and this has a voltage of 1.07 volts. Okay, so this is your these are your electrode, your standard electrode potentials. Okay, so with this we'll also look at the molar concentration. So for your anode, your molar concentration is 0.02 moles. Okay, and your cathode will be 0.1 moles. Okay, and your molecular mass, so which I'll write here as M cathode and M anode. So your M cathode will be 180.7 and M anode will be 78.97. Okay, so with these values, please do find out the three values that we had seen so far. That is cell energy, cell potential, and cell capacity. Okay, so you can just take 5 or 10 minutes to find out the answer, and you can just type it up in the chat box, and I will verify if the answers are right. Okay. So please do remember that K is equal to ratio of cathode concentration to anode. And don't forget to use natural log. Please don't use log to the base 10, you'll get the wrong answer. Instead use ln, natural log. Okay, so please keep this in mind. Okay, so has anyone been able to get the answers so far? Am I audible? Yes, I'm just waiting for some answers. So let me just write down the answer over here. So you can just verify with what you've got. So your cell potential will be So I'll write here E cell will be 4.089 volts. Okay, your cell capacity will be 744 milliamp hours. Okay, and your energy, your cell energy will be 3.03 watt hours. Okay, so these are the three different values that you would get. So if someone can confirm that these are the values, has anyone got these values so far? Okay, I see one person. Okay, so what about others? Have you all been able to follow the set of equations and numericals so far? So if anybody has any problems solving this equation. Okay, so you got the right solutions. Okay, that's great. Anybody else who's got the same answers? I just have to verify before I proceed to the next one. Okay, just wait for 2 more minutes. Molecular mass. You'll not be finding out the molecular mass. This is actually, these are just standard values for each element. But in these calculations, we will not be calculating the molecular mass. Instead, we will just be using that to calculate the capacity. That's it. So your capacity would be okay. So that's your cathode capacity, and similar to this, you'll also have anode capacity, which is NF by molecular mass of anode. Okay. So using the equations that I had showed you in the previous slide, that will be your cathode capacity into anode capacity divided by anode capacity plus cathode capacity. So if you take this, this will be your final cell capacity. Okay. So we will not be finding out the molecular mass. That's actually like out of the scope as of now. So you can use this equation to find your total capacity. Okay, so then I will proceed to the next point. Okay, so with these values, we will then find out just as a simple example, we will just find out how to calculate the total number of cells required for a battery pack based on number of cells in series and also the number of cells in parallel. Okay, so first and foremost, in order to find out your total number of cells in series, we must first know what is your required battery pack voltage. So what is the what kind of battery packages we are trying to design, and what is the voltage of each cell. Okay, so let's say that just as an example, let's take that we are trying to design a battery pack of 48 volts. Okay, and based on our previous calculations for lithium metal oxide, right? So LMO, we'll take that our individual cell voltage to be 4.089. Okay, so this would give us how many cells in series? This would give us roughly 12 cells. Okay, so the number would be 11.7. Okay, but we will round this off to 12. So 12 cells in series. Okay, and to find out the number of cells in parallel, we need to know the battery pack power. Okay, so to what power it is we're trying to design it for. So again, as a simple example, let's take that we're trying to design a standard battery pack power of 2 kilowatts. Okay, So that's nothing but 2000 watts. Okay, divided by individual cell power. Okay, so again, in this example, let's take the power to be the product of voltage and current. So that will be your 4.809, that is your standard, your total cell voltage, into, let's say that the cell is capable of giving out a total amount of current of say 2 amps. Okay, this is just as an example. Of course, higher powered cells will have more amount of current that can be given out. But for simplicity, let's take it as 2 amps into number of cells in series of, that is nothing but 12. Okay, so this will give a total number of cells in parallel as 21 number of cells in parallel. Okay, so using these two values, so number of cells in series and parallel, if you take the product of these two from here, okay, so 12 into 21, so this would give you 252 cells. Okay, so generally, when we are calculating the total number of cells, we don't leave it at this number. Instead, we will take some safety margin or some factor of safety. Okay, and we will take extra, take some few extra numbers at hand, and instead we will choose a round number of 260 cells. Okay, so given the specifications we obtained from the lithium metal oxide type cell, okay, so 4.089, based on the cell voltage, we are able to find out the total number of cells in series, number of cells in parallel, and the total number of cells. Okay, so 260 cells is what will be needed. Okay, and with this number, we will also perform some basic mass and volume calculations. Okay, so let's take the mass of one lithium ion cell. So as per the manufacturer data sheets, usually it will be mentioned that a simple 18650 lithium ion cell would weigh around 45 grams. So 18650 is one of the formats. So basically what that means is 18 is the diameter of the cell, 65 is the height of the cell. Okay, and the 0 stands for cylindrical. Okay, so 18650, this is what the designation means. And if you see the manufacturer, the standard chart that has been provided by the manufacturer, you will notice that most of your lithium ion cells that are of 18650 format weigh about 45 grams. Okay, so 45, of course, like plus minus will be there. So 45, 47 grams maybe. But as an average, it will weigh 45 grams. So if you convert this into kilograms, it will be 45 by 1000, 0.045 kilograms. Okay, so with this number, we'll then be able to find out your total mass of the battery pack. Okay, so we estimated 260 number of cells, right? So mass of one cell will be 0.045 into 260. Okay, so if someone can verify this number, this should give you a mass of 12 kilograms, if I'm right. Yeah, that's correct. You will get 11.7 kgs, so you can just round that off to 12 kilograms. Okay, and if you have to find out the volume, so what you're going to have to do, you will know the volume equation here. So simplified, we can use pi r squared h here. So we know radius is basically 18 by 2, right? So radius will be 9 millimeters. Okay, so if you were to convert this to meters, it will be 9 by 1000. So that will be 0.045. 0.009 meter. Okay. And your height. So this is your radius. The height will then be 65 by 1000. So 0.065 meter. Yeah. So, so volume of one cell will then be pi into 0.009 square into, okay, so this will be a total volume and it will be in meter cube. Okay, so can someone confirm this value over here? So it should give you a value of 1.07 into 10 raised to minus 6. Okay, so this will be your volume of one cell. Okay, so if you were to find out the total volume, it will be nothing but your volume of one cell into this. So your total volume, which I'll write here as V total, is nothing but 260 Okay. I think there's this mistake. Yes, it is 1.65 into 10 raised to. Yeah. So it will be 1.65 into 10 raised to minus 5. Yeah, that is correct. So then let's make that correction here. So 1.65 into 10 raised to minus 5. So your final answer would then be, so 4.29 into 10 raised to minus 3. Yeah, meter cube. Yes. So this is your total volume in terms of meter cube, right? So usually you would not be expressing this in meter cube. You'll express this in liters. Okay. So that would be, we know that 1000 liters is equal to 1 meter cube. Okay. So 4.29 into 10 raised to minus 3 meter cube would give 4.29 liters. Okay. So yeah, this is your final answer. So this is your total volume of the battery pack given the total number of cells. Okay. So I hope that everyone has followed. Has everyone got the same answer? So yeah, I see one person has, yeah, it's correct. Yes, 4.29 liters. Yeah, that is correct. So yeah, these are your final values when you're trying to calculate the total mass of the cell and total volume of the cell. Okay. So yeah, with that, we have come to end of today's session. So these are all of the basic points that I had to show all of you. So just as a practice, or probably as some sort of a mini assignment, you can try the same values with different values of currents. Okay. So say we had taken an example of 2 amps. So maybe you can try something like 7 amps. Okay. So try to find out the number of cells in parallel and try to see if you can find out what are the cell potentials, energies, and capacities for different chemistries. Okay, say for example, lead acid, nickel cadmium, right? So you can just try out this and you can see what is the differences in the size of the battery pack that you will get. Yeah. So for lead acid and for nickel cadmium, what would be the reactions and what would be your total cell potential as per the Nernst equation, and what is the total mass and volume of the battery pack. Yeah. So maybe you can just try this out. You'd be able to find a lot of these values in the internet. You'd be able to find out what is the lead acid constituents. You'd be able to find out what is the cathode and anode voltages, the standard cell potentials, and also the standard reactions. Okay. So yes, thank you for attending today's session, guys. This is the end of today's session, and now we can have a simple Q&A session. Okay. So